Hello everyone, my name is Yashaswini. In this video, we are going to see about the introduction to 2D and 3D graphics from the subject called Computer Graphics and Image Processing. Introduction to two-dimensional and three-dimensional graphics. Graphics are the visual component of computer-generated imagery and which include both two-dimensional and three-dimensional representation. Two-dimensional graphics, which mainly focuses on flat, planar images, while the three-dimensional graphics, which create the illusion of depth and volume. Understanding the fundamentals of two-dimensional and three-dimensional graphics is very essential for developing visually compelling applications, games, and digital art. This introductory section will provide an overview for both the concepts and principles that underlie these two domains. Now we will see the fundamentals of OpenGL. OpenGL represents Open Graphics Library, which is a powerful cross-platform API for rendering two-dimensional and three-dimensional vector graphics. It provides a standardized set of functions and commands that allow developers to create complex graphical environments. In this section, we will explore the core components of OpenGL, including the graphics pipeline, vertex and fragments, shaders, and the rendering process. We will also discuss how OpenGL abstracts away the underlying hardware details, allowing developers to focus on the high level design and implementation of their graphics intensive application. Graphics pipeline. The OpenGL graphics pipeline is a series of stages that transform three-dimensional scene data into a 2D image. This includes vertex processing, rasterization, and fragment processing, all of which can be customized using shaders. Shaders. Shaders are small programs that run on the graphics programming unit and are responsible for transforming vertices and process fragments. They allow for advanced rendering techniques like lighting, texturing, and special effects. Rendering process. The rendering process in OpenGL involves submitting geometric data, setting up the appropriate rendering states, and invoking drawing commands. This process is highly optimized for effective GPU utilization and can be customized to achieve desired usual visual effects. Two-dimensional graphics with OpenGL. While OpenGL is primarily known for its 3D rendering capabilities, it also provides robust support for two-dimensional graphics. In this section, we will explore the techniques and best practices for creating two-dimensional applications using OpenGL. We will cover topics such as orthographic projection, sprite rendering, and text rendering, and 2D animations. You will learn how to leverage OpenGL's efficient drawing commands and state management to build engaging two-dimensional user interfaces, games, and data visualization. Orthographic projection. Orthographic projection is a technique used in two-dimensional graphics, which is used to create a flat, non-perspective view of a scene. This allows for precise control over the positioning and scaling of two-dimensional elements. Sprite rendering. Sprite rendering is a common approach for displaying two-dimensional images such as characters, objects, or user interface elements. OpenGL provides efficient methods for loading, transforming, and rendering sprites. And then the third one is the text rendering. OpenGL supports the rendering of text, which is essential for creating user interfaces and data visualizations. Developers can use bitmap fonts or vector based fonts to display text with high quality and customization. 3D rendering with OpenGL. Moving beyond two-dimensional graphics, OpenGL's true strength lies in its ability to create immense three-dimensional environments. In this section, we will delve into the techniques and best practices for three-dimensional rendering using OpenGL. You will learn how to work with three-dimensional geometric primitives set up camera and lighting systems, and apply perspective projections. We will also explore advanced 3D rendering techniques such as model loading, texture mapping, and material properties to create visually stunning 3D scenes. 3D primitives. OpenGL provides a variety of 3D geometric primitives such as vertices, lines, triangles, and polygons that can be combined to create complex 3D models. Mastering the use of these primitives is essential for building 3D scenes. Camera and lighting. Effective 3D rendering requires the proper setup of camera and lighting system. OpenGL allows developers to define the camera position, orientation, and projection, as well as the type, position, and properties of light sources. And the third one is perspective projection. Perspective projection is a technique that stimulates the way the human eye perceives depth and distance in a 3D scene. OpenGL's perspective projection capabilities enables the creation of realistic 3D environments. Lighting and shading in OpenGL. Lighting and shading are fundamental components of three-dimensional graphics as they determine how surfaces and objects are illuminated and rendered. In this section, we will explore the various lighting models and shading techniques available in OpenGL. You will learn how to set up and configure different types of light sources, including ambient, directional, and point lights. We will also dive into the implementation of Phong and Blindfong shading models, which are widely used for realistic surface rendering. First one is lighting models. OpenGL supports various lighting models, including ambient, directional, and point lights, each with its own unique properties and effects on the 3D scene. Fog shading. Fog shading model is a widely used technique that calculates the color of a surface based on the interactive of light surface normal and viewer position. Blink-Fong shading. The Blink-Fong shading model is a computational efficient alternative to fog shading which provides similar visual results with less processing power. And then the fourth one is normal mapping. Normal mapping is a technique that uses a texture to store surface normal information, allowing for the creation of detailed and realistic 3D surfaces without increasing the geometric complexity. Textures and materials in OpenGL. Textures and materials play a crucial role in enhancing the realism and visual appeal of three-dimensional graphics. In this section, we will explore how to work with textures and materials in OpenGL. You will learn about texture mapping, which allows you to apply two-dimensional image to three-dimensional surface, and material properties, which defines the appearance of an object surface. We will also discuss advanced texture techniques such as multi-texturing and texture compression to optimize performance and create visually stunning three-dimensional scenes. The first one is the texture mapping. The texture mapping is a process of applying two-dimensional images known as textures to the surface of three-dimensional models. This allows for the addition of detailed surface patterns, color, and visual effects. And then multi-texturing. Multi-texturing is a technique of applying multiple textures to a single surface, enabling to creation of complex and detailed surface patterns and effects. Material properties. Material properties such as diffuse color, specular color, or shininess defines the appearance of an object surface. Adjusting these properties can create a wide range of visual effects for matte and glossy surface. Texture compression. Texture compression techniques such as DXT and ETC reduce the memory footprints of textures, allowing for the use of higher resolution images without sacrificing performance. Transformations and coordinate system. Transformations and coordinate systems are fundamental concepts in three-dimensional graphics as they define how objects and cameras are positioned, and oriented within a scene. In this section, we will dwell into the various of transformation available in OpenGL, including translation, rotation, and scaling. We will also explore how to work with different coordinate systems such as world, view, and projection and understand their role in rendering process. By mastering these concepts, you will be able to create dynamic and visually compelling 3D scenes. The first one is the translation, which is a process of moving an object or a camera to a new position within a three-dimensional scene. The second one is the rotation, which is a process of changing the orientation of an object or camera around one or more of its axis. The third one is scaling, which is a process of resizing an object either uniformly to a specific axis to change its size within the three-dimensional scene. Now we will see advanced OpenGL techniques. As you progress in your OpenGL journey, you will encounter a wide range of advanced techniques and features that can evaluate your three-dimensional graphics to new heights. In this final section, we will explore some of these advanced topics, including fragment shaders, geometric shaders, and frame buffer objects. You will learn how to leverage these powerful tools to create dynamic effects, procedural geometry, and off-screen rendering, all while optimizing your OpenGL applications for maximum performance and visual quality. We have fragment shaders, geometric shaders, and frame buffer objects. In fragment shaders, which are the type of programmable shaders that operate on individual pixels, allowing for complex pixel effects and advanced surface rendering. In geometric shaders, which are powerful features that allow you to create, modify, and discard geometric primitives during the rendering process, enabling procedural geometry generation. Frame buffer objects, which provide the ability to render the off-screen textures, enabling advanced renders techniques like processing, shadow mapping, and deferred shading. This is all about the introduction to two-dimensional and three-dimensional graphics. I hope the video was informative for you all. Thank you for watching.